All right, today we're going to start with chapter 13. Now, chapter 13 is basically where we're going to look at different circuits, all right? We had a look at the inverting amplifier, the non-inverting amplifier, and the voltage follower, all right? Now we're going to look at applications and some different circuits, all right? Adders and things like that. Now, the first thing is comparators. 13.1 is comparator. What does a comparator do? It compares certain things. Voltage levels, all right. The first one is the op-amp is a zero-level detector. Why do we call it a zero-level detector? Because it's going to compare my input signal with 0 volts, all right. My reference is 0. It's going to compare the input signal, all right. Now you can see the inverting input is connected to 0. That means, what can I say about my input signal and my output signal? Will they be in phase or out of phase? They will be in phase because the input is at my non-inverting input. If I reverse the inputs, then they're going to be 180 degrees out of phase. All right, let's have a look. First of all, I said my reference is 0. When my input signal goes above my reference, it can be milli or microvolts above the reference. What happens? The output will shoot up positive. To what value? To the maximum value. Why the maximum value? Why will it go to the maximum value? There's no feedback. All right. What determines the maximum value? My supply determines the maximum value. All right. Everybody with me? Now, during this whole time, it's positive. At that point, what happens? It goes negative. Goes negative respect to my reference. What will happen then? It will shoot down negative and stay negative for that whole duration of time. That means, what does the circuit do? It compares the input signal with 0 volts. Any questions? The next we're going to talk about is non-zero level detectors. Why non-zero? Because my reference is not going to be 0 anymore. All right. If you look at this first one here, there I got a battery with a reference voltage. What is my reference voltage? It's positive. All right. Now, again, what I'm going to do, I'm going to compare the input signal with my reference. My reference is a positive voltage on the non-inverting input. Let's have a look. At this point, what is my input signal with respect to my reference? What is my input signal with respect to my reference? I repeat, what is the input signal with respect to reference? Negative or positive? It should be one of the two. Is it positive or negative? At this point, what does my input signal do with respect to my reference? Whoa. Hey, you must start waking up. You S3s, you must wake up. My input signal is negative with respect to my reference. 0 volts is negative with respect to a positive voltage. All right. If I apply a negative in here, what should the output be? It should be negative. What is the output here? Negative. I see some blank faces in this class. You know what's blank faces? The lights are on, but nobody is at the home. Hey? I repeat again. Input signal here is 0. 0 is negative respect to my reference. Negative at my non-inverting input will give me what out? Negative. Maximum negative. Then my input signal start eating. At that point, my input signal becomes positive with respect to my reference. All right. When it becomes positive respect to my reference, what will happen? It will shoot up positive and will stay positive for that duration of time. At that point, my input signal becomes negative. When it becomes negative, it will shoot down negative and stay negative for that duration of time. At that point, the input signal becomes positive where will the output go? It will go positive again. You with me? It compares the input signal with my reference. Here I just got a voltage divider, also giving me a positive reference voltage there. Because it's positive there, give me a positive reference voltage here. Here we got a Zener diode, same circuit. Zener diode will give me a reference voltage. Any questions? Let's have a look at example 13.1. They say the input signal in figure 13.3a is applied to a comparator in figure 13.3b. Draw the output showing the proper relationship to the input signal. Assume the maximum output levels of the comparator are plus minus 14 volts. Now that plus minus 14 volts is due to my supply. All right. Input signal from 0, maximum positive and maximum negative minus 5. Positive plus 5, negative minus 5. All right. I got a voltage divider. I got a voltage divider there, a 8K2 and a 1K. Where will my reference voltage be? It will be across the 2 kilo ohm. All right. That's why I can say V reference R2 over R1 plus R2 times 15. And that will give me 1,63 volts. That means my reference voltage will be round about here, 1,63 volts. All right, you with me? All right. My input signal here, at that point, my input signal is 0 volts, all right. What is 0 with respect to 1,63 volts? It's negative. And my input was at the non-inverting input, that's why I will have minus 14 volts. At that point, what happens? The input signal becomes more positive than 1,63 volts. Output will shoot up positive and stay positive for that duration of time. At that point, input signal becomes negative with respect to 1,63 volts. Output will shoot down negative and stay negative for that whole duration of time. All right. That's what a comparator is doing. It compares voltages. All right. Sometimes it's more clever than students because that thing will always give you the right answer. You will give me the wrong answer. Eh? Right or wrong? I know what I'm talking about. All right. The next part of the work, effects of input noise on comparator operation. Now we know we got a certain reference and my input signal goes through that reference value. The comparator is going to switch each time. All right. When it changes that, the comparator is going to switch. Now let's say I got a signal. On top of that signal there's noise. That means when that noise goes through the 0 line, it's going to switch. And that can give us switching times we don't want. All right. And to illustrate that, here we got a signal. You can see there it goes through 0. My reference is 0. All right. There it goes through 0. There it goes through 0. There it goes through 0. We have a look there. There. There's 3 positions where that thing going to change its output state because it goes through the 0. To illustrate that nicely, you can see here, there's 1, 2, 3, 4, 5 positions where my signal goes through 0, through my reference, and then each time the output is going to change, all right? See, there's 1, 2, 3 positions. There are 3 positions going to change state, and also there's going to change state, all right? Due to the noise, all right? Now, we can do certain things to eliminate that problem, and then we're going to talk about hysteresis. We're going to apply positive feedback to the circuit, and we're going to eliminate this problem of noise. There they say, we're going to discuss this, reducing noise effects with hysteresis, all right? That's one thing we're going to apply to get rid of the noise effect. We're going to make use of hysteresis. Now, if we look at this circuit here, what will you say? Is that positive feedback or negative feedback? That is positive feedback, all right? Because my output is taken to my non-inverting input, all right? Not to my inverting input, to my non-inverting input. That will give me positive feedback. But what will happen? I will change the reference. You can see here, when there's an output, there's going to be a volt drop across R2. All right, the volt drop across R1 and across R2. But this volt drop across R2 will determine what? My reference, all right? It's going to change my reference, all right? Because now I'm not going to have 0, what the case may be, but I will have a certain voltage there. And that's why they say the upper trigger point, VUTP stands for the upper trigger point, is going to be equal to R2 over R1 plus R2 times V out maximum. Positive because that thing will always go to the maximum values because there's no negative feedback, all right? And then for the lower trigger point, it's going to be R2 over R1 plus R2 times minus V out max, all right? For the lower trigger point, I'll quickly show it to you. There's the formula for the lower trigger point, R2 over R1 plus R2 times minus V out maximum, all right? All right, if we have a look at this point here, what is my signal with respect to my reference? Now you can see in this case, my signal is negative with respect to my reference. That means if it's negative at my inverting input, where will the output go? Where will the output go? Positive, all right. Now you can see it's positive maximum. When it's positive maximum, I will have a positive voltage here, all right? And that will give me my upper trigger point. Now the signal increases. When it reaches the upper trigger point, what happens? Then the signal becomes more positive than my reference, or more positive than this upper trigger voltage. When it becomes more positive, where will the output go? Shoot down negative to minus V maximum. And now it will stay there the whole time until this input signal becomes negative with respect to that negative voltage. More negative, right? Because this voltage now is a negative voltage, that value, when it becomes more negative, what happens then? Then it will shoot up positive again, all right? And that is hysteresis. Hysteresis is the difference between those two voltages. The voltage, the upper trigger point and the lower trigger point will give me my hysteresis. That will bring us to this formula. There they tell us hysteresis is the upper trigger point minus the lower trigger point voltages. All right? You with me? All right, here's an example. Let's quickly have a look at this example. Example 13.2. Determine the upper and lower trigger points for the comparator in figure 13.9. Assume that plus V out max is plus 5 volts and minus V out max is minus 5 volts. And you can see the ratio of these two resistors are exactly the same. Each one of them are 100 kilo ohms. That means it's going to be 0.5 times 5 volt will give me plus 2.5 volts for the upper trigger point, and the lower trigger point will be 0.5 minus 5 volts, and that will give me minus 2.5 volts. All right. What will your hysteresis be? What will the hysteresis be? It will be 5. All right. All right, up till now, what happened? It will always go to the limits, to the maximum voltages, right? What determined the maximum voltage? The supply. We got rid of the noise by making use of hysteresis. Now we're going to go and look at bounding. That means we're going to limit the output voltage to a certain level, and that's why they talk about output bounding. All right, there's a circuit with output bounding. We got a Zenodiode there. Now electronics 2. No, where did you do Zenas? Electronics 1. Yes, electronics 1. That means you know all that work. How do we normally use a Zenodiode? I'm going to ask all my latecomer friends. Those are for the first time in my class. Why? How do we normally use a Zenodiode? Forward biased or reverse biased? Hey. Reverse biased. You sure? What are you saying? Huh? Oh, not the first time. Oh. What are you saying? Reverse bias. All right, we use a Zenodiode normally reverse bias. Can we use a Zenodiode forward biased? I'm asked, can we use a Zenodiode forward biased? Yes. It will act like a normal diode. That means when a Zenodiode is forward biased, the volt drop across it will be around about 0.7 volts. When it's reverse biased, the volt drop across it will be the Zener voltage. Is manufactured to give you 5 volts or 5.3 volts or what the case may be. It will give us that reverse bias voltage as long as you limit the current so that your current is less than your maximum power rating of the device. Otherwise, it will go up in smoke. All right. All right. Output bounding. Let's quickly go and explain this. What's happening? All right. In this circuit, what is my reference? 0. All right. My reference is 0. Now I apply this input sine wave. I know the current's going to flow in that direction because current flow from positive to negative. When it's flowing that direction, what can I say about the Zenodiode? Is it forward biased or reverse biased? I got the reverse, I got forward, or maybe forward reverse, I don't know. All right, it's forward biased. Always, if you don't know, this arrow, all the arrows in your components indicate what? The direction of conventional current flow. And how does conventional current flow? It flows from positive to negative. That means the input current is going to flow in that direction. Exactly the same current must flow in that direction. All right. The Zenodiode is forward biased. When a Zenodiode is forward biased, what's the volt drop between the anode and the cathode? It's 0.7 volts. That's why that is at 0. The output must go negative to get that current to flow. That's why it's minus 0.7 volts. All right. For the positive cycle. For the negative cycle, what's going to happen? The negative cycle, this current is going to flow in that direction. The op-amp must adjust its output in such a direction to get that current also to flow in the same direction. All right. When the current is flowing opposite the arrow, the Zenodiode is forward biased or reverse biased? It's reverse biased. When it's reverse biased, what will we get? The Zener voltage across it, all right? And the output will be positive, all right, plus Vz. Now it's going to cut it off at the Zener voltage. You bound it to the Zener voltage. Otherwise, it go to the maximum value. Everybody with me? Any questions? Are you happy? All right, let's have a look at the next one. That one, we turn the Zener diode around, all right? During my positive cycle, current's flowing in that direction, flowing against the arrow. Zener diode is reverse biased. The output will go to minus Vz because that is at 0. To get the current to flow in that direction, it must go negative, all right? Because that point is at 0. My output must be more negative than 0 volts. Otherwise, I won't get the current flow in that direction. All right? That's for the positive cycle. For the negative cycle, the current's going to flow in that direction. That current's flowing in that direction. 0 volts there. The output must go positive to what value? 0.7 volts, because the Zener diode is forward biased. You must talk. If there's any questions, you're welcome to ask. Because next time I ask the questions. All right, the last one. In this case, we got two Zener diodes back to back, all right? That means the one Zener diode will be forward biased, the other one will be reverse biased, and vice versa, all right? Let's consider positive cycle. Positive cycle, current flowing in that direction, that current must flow also in that direction. D1 is what? Reverse biased. D2 is forward biased. That's why they say minus Vz1 minus 0.7 volts. That will be my output. All right. The negative cycle, what happens then? The current is going to flow in that direction. That current is going to flow in that direction. D2 is reverse biased. D1 is forward biased. That's why plus Vz plus 0.7 volts. All right. Now we bound them to both sides. All right. For your positive cycle as well as your negative cycle. Any questions? Before we go to the next example. All right. In this case, this example is more on the standard of my students in this class. In this case, we're going to look at hysteresis and output bounding. That means on this circuit, we're going to apply hysteresis and output bounding. All right, we're going to incorporate both those circuits. They say determine the output voltage waveform for figure 13.13. This comparator has both hysteresis and Zener bounding. The voltage across D1 and D2 in either direction is 4,7 volts plus 0,7. It's equal to 5.4 volts. That means 4,7 plus 0.7 will give me 5.4. In one case it's going to be positive, and the other case it's going to be negative. This is because one Zener is always forward biased with a drop of 0.7 volts, when the other one is in breakdown. All right. All right, they show the input voltage plus 5, minus 0.5 volts, minus 5 volts. And there's my resistors for my hysteresis, 100K and a 4,7 kilo ohm. And they say the voltage at the inverting of the op amp, VR is equal to plus minus 5.4 volts. Since differential voltage is neglectable, the voltage at the non-inverting input is also approximately 5.4 volts. What have I told you right in the beginning when we start with the op amps? I've told you the op amp always try to make the voltage difference equal to what? 0. All right. That's why they make this statement. Now VR1 is equal to V out minus, all right? Because the output voltage is going to be equal to the total volt drop across here, all right? That means that volt drop plus that volt drop will give me my output voltage. That's why they say VR1 is equal to V out minus V out plus minus 5.4 volts, and that is equal to 5.4 volt plus minus, because depending what my input signal will be, one time it will be plus positive, the other time it will be negative. Then we can work out R1, because now we must remember, is there any current flowing in here? Is there any current flowing in there? No. The amount of current that will flow in there is neglectable. Why? We've got a very high input impedance, all right? That's why they say VR1 is equal to IR1 is VR1 divided by R1, and that gives me plus minus 54 microamps. And they say, since the non-inverting input current is neglectable, what I already mentioned, then I can say IR2 is equal to IR1 is equal to plus minus 54 microamps. You can neglect that current because it's neglectable. We got that very high input impedance. Then I can work out VR2, and that will give me plus minus 2.54 volts. And I know V out is equal to VR1 plus VR2, and that will be plus minus 7.94 volts. All right, that's going to be my output voltage. If I've got the output voltage, what can I do? I can go and determine the upper trigger point, and I can go and determine the lower trigger point. All right. Upper trigger point is equal to R2 over R1 plus R2 times V out, and that will give me plus 2.54 volts, and the lower trigger point will be minus 2.54 volts. All right. And there's my output. The input was, as I already mentioned, plus 5 volts to minus 5 volts, sine wave. And there's my upper trigger point, and there's my lower trigger point. And that means when my signal here is negative with respect to my upper trigger point, I will have positive because I'm using the inverting input. When my input signal goes below my lower trigger point, then it's negative, then it'll shoot up positive. All right. Any questions? No questions? Hey, you're very clever students. All right, the next part of the work is comparator applications. We're going to look at comparator applications. All right, that circuit is called the over temperature sensing circuit. Over temperature sensing circuit. All right, where we use this op amp as a comparator. All right. Now I'm going to do it very practical. The whole description is in the book. I'm going to do it very practical. I'm going to put some voltage values in there, and we can go and work through the circuit. All right. First of all, if you look at this, this is a bridge connection. All right. Here's one arm, and there's the other arm. And if I look at this, R3 and R4, what do they do in the circuit? If I look at R3 and R4, what are they doing in the circuit? What? All right, so voltage divider. But what is this voltage divider going to do? What does it give us? It will give us a reference. Thank you. That will give us a reference voltage, a reference to my comparator. All right. Because that value, is it going to change? No, it's going to stay the same. On this arm here, we've got an adjustment there, and we've got a thermistor. Now, what will the thermistor do? It will sense the temperature, all right? And this thermistor will have a negative temperature coefficient. That means if the temperature increase, what happened to the resistance? The resistance decrease, all right? I repeat, when the temperature increase, the resistance value decrease, all right? Now, let's make it interesting. Right, now I can write. Let's assume we make our reference voltage 5 volts. This voltage divider here give us 5 volts. Right, seems this to me this thing, I'll tell you. Let's assume we make the reference voltage 5 volts there. 5 volts at this point. That's going to stay constant, all right? All right, let's assume the voltage here, with a certain temperature, I adjust, let's say we want this thing to switch when my temperature reaches 100 degrees Celsius, all right? Let's assume the voltage here is around about 4.5 volts. Now, if I got 4.5 volts there and I got 5 volts there, what is 4.5 volts with respect to 5? It's negative, all right. Negative at my non-inverting input will give me what out? It will give me negative out. The transistor will be off, all right. It won't switch. But now, let's say my temperature increases in the direction of 100 degrees Celsius. This resistance will do what? It will drop. When that resistance drops, what will happen to the voltage here? It will start increasing, all right. Now it increases slowly. When this voltage here becomes larger than 5 volts, let's say it becomes 5,01 volts, what happens then? Now this becomes more positive than that. What will the output do of the op-amp? Will it go positive or negative? It will go positive, all right. It will cause a base emitter current to flow. When the base emitter current flow, there will be a collector emitter current flowing, all right. It will energize the coil of the relay and will basically change the state of my contactors and give an alarm or what the case may be, all right. And this is here to adjust your set point. You can adjust that for different temperatures to switch. But it actually, I got a reference voltage, and that thermistor, when that voltage there becomes higher than my reference, the transistor will switch. All right. All right, what is the purpose of this diode? I don't mention it in the book, but I think it's quite important. What is the purpose of this diode? Anybody? Anybody? The purpose of this diode, you know, when the current is flowing in that direction, is the diode forward biased or reverse biased? It's reverse biased. That means I can take it out. It's like an open circuit. Won't do anything. But what happens when my transistors switch off? All right. When this transistor turns off, here we got a magnetic flux. You know what's a magnetic flux? Now we go back again to engineering 1. When that magnetic flux collapses, it cuts the conductors, all right? And it can generate an EMF that's much higher than my supply, all right? And the polarity of that is the opposite way around. When it was positive, negative, when that magnetic flux collapses, it becomes positive, negative, all right? And the purpose of the diode is to short out that voltage, and it protects my transistor. Because if that voltage becomes too high, it will basically damage my transistor. All right, you with me? Is there any questions? Any questions? All right, the next circuit. Now we're going to look at an analog to digital converter, A to D. That means I'll take an analog signal and convert it to a digital signal. Where in the lab did you use some equipment that was doing basically that? Taking an analog signal, convert it to a digital signal. In the electronics lab. You were working in the electronics lab. Huh? No, what does the oscilloscope give me? You put an analog signal and you basically see an analog signal. Anybody? What about the multimeter on the voltage scale? If you put a multimeter on the voltage scale, what do you measure? You measure an analog signal, a voltage signal. And what is the readout? Digital, right. There's basically an analog to digital converter. The old meters with the moving point, that was basically an analog meter because it will give you a variation of the needle, all right. Today it's so easy, you just read off so many volts, but all right. Alright, let's quickly have a look at this analog to digital converter. They talk about a simultaneous analog to digital converter. Let's make it easy for ourselves. Let's assume, you see here's a lot of, that's basically voltage divider, a lot of different resistors connected in series, alright? We got 1, 2, 3, 4, 5, 6, 7, 8 resistors, alright? Let's assume we make our reference voltage 8 volts, alright? If I got 8 volts there, it's going to be 1 volt, 1 volt, 1 volt. If I measure across each resistor, I'm going to measure 1 volt, alright? That's like changing the scale on your multimeter. If you change your scale, you're going to get different voltages across these resistors, alright? But now let's work with 1 volt for explanation purposes. 1, 1, 1, 1. That means if I measure with respect to my reference, from there to there I will measure 1 volt. From there to there I will measure 2, 3, 4, 5, 6, 7, 8. All right. Now let's assume I apply 1, 1 volt. I apply 1, 1 volt here at the input. That means that all these non-inverting inputs will be what? 1, 1 volt, because you can see all of them being connected together. All right. Now, there's 1 volt. Here's 1, 1 volt. What is 1, 1 with respect to 1? It's more positive. That means this comparator will give me a high output. All right. A high output to my priority encoder. All these other ones, there's going to be 2 volts. What is 1, 1 respect to 2? Negative. It will give me a negative. It will give me a negative or low. Because a low value. All right. That means there I will only have that one as a high output, and it will give me a binary output, this priority encoder. All right. You with me? Let's go and do something else. Let's say we put 5 volts, or let's say 5.2 volts in, right? If I put 5.2 volts, that means on all these inputs there's going to be 5.2 volts. All right, there's 1, 2, 3, 4, 5. That means this output here will be, that will be high. All right. And then those will be low and low. All right. And that's how he determines the correct output. It's just comparators with a lot of resistors in series. Everybody with me? We're going to look at example 13.4, determine the binary number sequence for the 3-digit simultaneous ADC in figure 13.16 for the input signal in figure 13.17. The sampling pulses encoder enable shown. Draw the resulting digital output waveforms. We look at the figure 13.17. That's a sampling analog signal. There's a sampling analog signal, a varying signal, and there's my encoder enable pulses. And we can see we sample there and we sample there. And then we go and look at figure 13.8, the encoder enable pulses. And there we got D2, D1, and D0. D0 is 1, D1 is 2, and D2 is 4. That means 2 to the power 0, 2 to the power 1, and 2 to the power 2. Then we get op amps that specific comparators, not like you can use any op amp as a comparator, but these specific comparators got special characteristics. The ones is the LM111 and the LM311 are examples of specific comparators that exhibit high switching speeds and other features not normally found on general type of op amp. Those comparators can operate with supply voltages from plus minus 15 to a single plus 5 volt. The open collector output provides a capability of driving loads that require voltages up to 50 volt referenced to ground or to supply voltages. An offset balancing input and a strobe input allow the output to be turned on or off regardless of the differential input. Here they show us also a few comparators with different reference voltages making use of a voltage divider. The first one got a positive reference voltage at the non-inverting input, and the second one got a negative reference voltage at the non-inverting input. Thank you.